Hello, my name is Steve Ives and I'm with the Synergex Professional Services Group. I'd like to welcome you to this presentation entitled Synergy Objects Part 1. This presentation is geared towards Synergy developers who wish to begin learning about object-oriented programming in Synergy, or towards developers who have experience developing with another OO language and want to learn how to use the OO techniques that they're already familiar with in Synergy language. The presentation is approximately 65 minutes long. If at any point you wish to stop and resume viewing at a later time, use the table of contents on the right to select the appropriate slide. The main objective for this session is to provide an overview of the support for object-oriented programming that was introduced to Synergy language in the 9.1.1 release. We'll start off by introducing and defining some of the main OO terms, like namespaces, classes, fields, methods and properties, and of course objects. We'll also discuss what strong prototyping is all about and how it can help you ensure the correct use of the classes and routines that you create. Then we'll move on to examine the syntax which allows you to use OO programming techniques in Synergy applications. For those of you that do not currently know about object-oriented programming in another language, this session should help you become familiar with the many terms and concepts used during OO development. For those of you that do already program in another object-oriented language, the first part of this session will act as a review, and then we'll go on to show the syntax for creating and using classes and objects in Synergy. Please bear in mind that this is an introductory session. We will cover classes and objects, fields, methods and properties, and show how to instantiate and use objects. We won't, however, get into more advanced OO capabilities like constructors and destructors, inheritance and overloading, overriding, and some of the other features that you can see listed on this slide. These are all things which are supported in Synergy language, and there are other things which we support that aren't listed on this slide, but attempting to cover everything in just one session would simply take too long. Prior to version 9, Synergy language was known as a procedural language. Rest assured that the new version 9 compiler still supports writing procedural programs, subroutines and functions, and will still continue to compile your existing applications. Using OO in Synergy is entirely optional. However, there are some good reasons for considering OO programming. The first is that writing with OO techniques usually results in more maintainable code. Now, everyone can write maintainable code in other non-OO languages. However, one of the features of OO is to keep the data together with its related routines that work on that data. So, if you have to change the data, this makes it easier to find and change the routines that work on that particular piece of data. Additionally, through features in the OO language, you can hide certain data or routines from the outside world, in essence making it private. So, if you need to adjust a private routine, you know that that routine is only used in certain places, making it much easier to analyze the impact of changing the particular routine. The next feature is to write more powerful code. Now, I'm not suggesting that you can't do everything in a procedural language that you can do in OO. You can certainly emulate the environment. However, OO has some built-in features such as inheritance, method overloading and method overriding that are very powerful, as you'll see in later sessions. The new compiler itself was written in an object-oriented language to allow it to take advantage of OO's power. Also, if you plan to take advantage of Synergy DE for .NET in the future, then you'll need to learn to use OO to take advantage of all of the features of the .NET framework. So, what is object-oriented programming? Well, what it boils down to really is that it's a way of programming where you model the software that you create based on the real-world things that your programs deal with. You can see some examples of these things on this slide. Person, employee, customer and supplier. These are all things that software applications could work on. And in some ways they're all kind of related. They all involve or represent people or organizations. Similarly, inventory item, package, shipment, address, sales order, purchase order, and payment are all things that an order processing application might work on. Each of these things, or objects, have attributes and also behaviors. Attributes define the characteristics of an object. For a person, some characteristics might be things like the color of their hair, their eye color, height, and weight. Behaviors of a person are the things that the person does, such as sleep, grow, eat. Here's an example of a sales order object. If you haven't done object-oriented programming before, then it may seem a little strange to think about a piece of paper as an object, and it may not be immediately obvious to you that a sales order has attributes and indeed behaviors, but it really does. The attributes of a sales order are things like order number, customer name, delivery address, and collection of items. To define the behaviors of a sales object, it helps to think of the things that are done to a sales order during its lifetime. When you think about it that way, it becomes clear that the behaviors of a sales order are things like adding and removing items, changing quantities, or even cancelling an order. In object-oriented programming, we build our applications to work with objects like these, and we describe those objects by writing source code that defines the attributes and behavior of those objects. The code that we write to describe an object is called a class. So, a class is a blueprint that defines an object's attributes and behaviors. To create an object, you first need to write source code which describes the attributes and behaviors of the object, and this source code is called a class. In a class, attributes are represented by data, which are defined as fields. Behaviors are represented by functionality that works on the data, which are defined as methods or properties in the class. Each class is given a name and groups together all of the attributes and behaviors in one definition that is later used to create an object. We collectively refer to the fields, methods, and properties of a class as members of the class. Fields represent the attributes of a class. So if we think back to the sales order example from earlier, some of the fields in a sales order class would be things like the order number, the customer name, the shipping address. Like variables in a record, fields have a name and a type. Some types, like alpha, decimal, and integer, also have an associated size. The type indicates what sort of memory the field represents. It could be a built-in synergy type, such as an I4, an A10, or it could be an extensible type, an object. The values associated with fields can be changed by methods and properties in the class, and depending on how the field is defined, possibly by external routines which are using the class. The fields in a class are collectively known as the instance data, with the exception of static fields, which we'll talk about in another session. We'll talk more about instances later, but in short, each object has its own data, or its own characteristics. For example, one person may have brown hair and blue eyes, while another person has black hair and brown eyes. Methods define the behaviors of a class. In our earlier sales order example, some methods could be add item, remove item, confirm order. Methods are like subroutines and functions in that you'll specify a name and an optional return type. They may have parameters associated with the method. They can also have data defined in their data division, and they have a procedure division, which includes the executable statements which define the functionality of the method. Methods are called from somewhere. Most of the time they're explicitly called, but there are some cases where methods are implicitly called because some event took place. Some of the special methods that get called implicitly are the constructor, which is called when an object is created from a class, and a destructor, which is called when the object is deleted. Most importantly, methods can operate on the object's data. Properties really are kind of a funny beast. It's hard to know whether to refer to them as attributes or behaviors. Properties are accessed like fields, and indeed they represent and expose data, but actually they call methods. Properties have a name and a type, just like a field, but they also have one or more methods that are used to either get the data or set the data. So when you access a property like you're setting a field, it calls the property's set method. When you access the property like you're getting the value of a field, the get method is called. Every property must have a get method, or a set method, or both. A special property, an indexer, also has parameters, but we'll talk about these in other sessions. It is sometimes hard to know when to use a property instead of just using a field. With experience, you'll come to realize that there are some situations where using a property over a field makes very good sense. For example, properties give you much greater control than fields. If you don't define a set method for a property, then the property becomes read-only. And if you don't define a get method, then the property is write-only. This level of control can't be achieved with simple fields. Since all value changes to a property come through the execution of a set method, sometimes programmers will add validation logic within the set method to ensure that the value being set is within a permissible range, or perhaps amongst a list of allowed values. It's also possible that the value of a property must be derived from some calculation based on a combination of other class fields. In this case, the get method could include logic to perform such calculations. In the future, when using Synergy DE for .NET, properties will also be the mechanism which facilitates things like design time binding of data to field forms, and much more. As a side note, some programmers resist using properties because of the additional overhead of calling a method to simply access a piece of data. However, in Synergy we've addressed that concern in many cases. If the compiler finds that the code in a property set or get method performs simple access to a field within the class, then it will optimize that property access into a simple field access. This means that Synergy programmers can take advantage of the features of properties, but in many cases avoid the additional runtime processing overhead typically associated with the use of properties. Another concept that you need to know about when using OO techniques is that of accessibility, which provides a mechanism to hide class members from the outside world. Each class member can have accessibility specified. Public accessibility means that that member can be accessed from anywhere without restriction. Private accessibility means that the member can only be accessed from within the same class, and it's not accessible from anywhere else. There is a third type of accessibility currently called protected, which means that the member can be accessed from within its own class or from within a derived class. However, we won't be getting into inheritance and derived classes in this session, so let's not worry about that one too much at this point. If a member does not have accessibility specified, then the default accessibility of private will apply. When designing a class, you need to think about where you want the members of the class, its fields, methods, and properties to be accessed from. If you only want the class member to be accessed from inside the same class, then you want an accessibility of private. Having private members makes it easier in the future to analyze the impact of potential change to that member, since you know the member can only be used from within that class. Remember that private accessibility is the default. If you wish to be able to call a method or manipulate a field or a property from outside of the class, then you must explicitly specify accessibility of public or protected for that member. Another concept new in Synergy version 9 is that of namespaces, which provide a way to logically group or organize classes by company or by functionality or perhaps by application. A namespace has a unique name. There are two main purposes for a namespace. One is to prevent naming collisions. For example, you may want to have a class called invoice in your accounts payable subsystem, but you might also need a different class called invoice in your accounts receivable application. You could simply give these two classes different names, but then the code which uses those classes becomes more complex and arguably less readable. A better solution is to define two namespaces, one for accounts payable and one for accounts receivable. Each of these namespaces can then include an invoice class. When referring to the classes, we use the class's full path name, which includes the namespace. Another important use of namespaces is that they are used when importing information about classes for strong prototyping reasons, which is required when using classes. We'll talk about more about this later in the session. By the way, we've reserved two namespaces, Synergex for our own classes in the Synergy DE products, and System to prevent problems down the road when using Synergy DE for .NET. Namespaces can be nested to provide logical subdivisions of classes. In this example, we have the AP and AR nested namespaces that are nested in the My Company namespace. In the example, invoice appears in both namespaces. Now these are different invoice classes. They're likely to have different class members. Since classes are part of a namespace, they are uniquely defined by their fully qualified name, which is the class name prepended with all of its outer namespaces. In most cases, when using a class, a user can simply specify the class name. However, let's say a user tries to use the invoice class above and has access to both of the namespaces AP and AR. Which invoice class gets selected? Well, it's a situation where specifying invoice alone is ambiguous. The compiler cannot tell if you mean AP's invoice class or AR's invoice class. How do you uniquely define it? You use its fully qualified name. But in this example, as long as you specify enough of the fully qualified name to make the identifier unique, then that would work. So ap.invoice will do the trick. Namespaces are also additive. Unlike class declarations, which must be all together in the same source code, all the classes which belong to a single namespace can be scattered across multiple source files, and they're added together just like you specified them together in one source file under the namespace declaration. This slide simply presents the same kind of information, just in a slightly more graphical manner. Here you can see an example of how namespaces can be nested, and within each namespace you can have different classes. Note that the invoice classes are part of both the AP and AR namespaces. The term prototype is also new to Synergy in version 9. A prototype is basically a stripped down version of a class, or subroutine, or function, or structure. A prototype includes the signatures of these things, but does not include any implementation information, no procedural code. The prototype is used by the compiler to allow it to know about all of the symbols which are available to it. I'd like to talk about the term local for a moment. Local means that the definition of a class or a subroutine or a function or a structure is defined within the same compilation unit. For example, if you're compiling 5 source files together at the same time, and one of those source files has a definition for a class, that class is said to be locally defined throughout all of the source in those 5 modules. When something is locally defined, the compiler uses that local definition to check calls to that class or subroutine or function, for example. For local classes and structures, a call that doesn't match the definition will generate a hard error. For local subroutines and functions, a call that doesn't match will give a warning. To change those warnings to hard errors, to ensure that your subroutines and functions are being used correctly, prototypes for the subroutine or function can be used. When non-local classes and structures are used, a prototype is required. Otherwise, a call will give an unresolved error since the compiler doesn't have the symbols for that class or structure available. To provide symbols for these, generate a prototype for the class or structure and then import that prototype. This will allow the compiler to resolve the call. One important fact about imports is that you import a namespace, and all members of that namespace get imported at the same time, meaning all the symbols for the classes, structures, subroutines and functions are added to the compilation. Note that an import of a namespace only imports that namespace, not its nested namespaces and not any outer namespaces. Okay, so we've introduced the main terminologies for some of the new things that are supported in Synergy version 9. Now we'll move on and expand on some of the things that we've talked about so far and show you how to actually define things like classes, fields, methods and properties in source code. The process for creating a class is very simple. The first step is to declare the namespace that you want your new class to belong to. If your requirements are simple, perhaps if you only have a single Synergy application, then perhaps your namespace will be your company name. If your requirements are more complex, then you may wish to design a hierarchical set of namespaces. Once you've declared the namespace that your new class will belong to, the next task is usually to declare the class itself. Then, within the class, you can add the members to the class, its fields, methods and properties that implement the desired attributes and behaviors for the new class. Once you've added members to the class, you're at a point where you can compile the class to see if all is well. When you're satisfied that the class is complete, or at least complete enough to start working with, you will generate a prototype for the class in order to be able to use the class from other routines or classes in your application. Strong prototyping is mandatory with classes. So here's our first look at a piece of real OO syntax. Namespaces are declared with the namespace end namespace statements. These statements surround members of the namespace, which might be classes, subroutines, functions, and structures. Notice that the namespace has a mandatory name and an optional nested namespaces separated by periods. This allows you to use nested namespaces, which we talked about earlier. It's also possible to declare one namespace entirely within another. This is just another way of declaring nested namespaces. On this slide we can see several examples of how namespaces can be declared, including the different ways in which namespaces can be nested inside one another. The first example declares a namespace called My Company. Any members, for example classes, which are defined within the main namespace, will be members of the My Company top-level namespace. In the second example in the middle of the slide, we again have the top-level namespace My Company, and it may contain members such as classes. We also have a nested namespace called AP. Members declared within the AP namespace statements are actually part of mycompany.ap. because AP is declared within My Company. Finally, the third example at the bottom of the slide shows an alternate way of declaring a nested namespace. Again, the mycompany.ap namespace. You don't have to use multiple namespace end namespace statements to achieve nested namespaces. Once we've declared a namespace, we can then start adding members to the namespace. And the main type of member we're interested in at the moment is a class. A class is declared using the class end class statements, and notice that the class has a mandatory name. Between the class and end class statements, we'll declare the members of the class, its variables, methods, and properties. Although it's not shown on this slide, remember that all classes must be declared within a namespace. It's also possible to declare a class within another class. This is called a nested class. When you do this, the outer class functions kind of like a nested namespace. It provides a way to uniquely identify the nested class, just like a namespace would. However, this subject is getting a little too advanced for this session, so let's not worry about that right now. Here's a simple example of the definition of a customer class within the namespace mycompany.ar. It's not possible to compile or use this class though, there wouldn't be much point. It doesn't actually contain any attributes or behaviors. Before the class is useful, we must add some members between the class and end class statements. Once we have a class, we can start to add members to define the class's attributes and behaviors. Let's start by looking at the most simple members, fields. Fields are added to a class in a similar way that you would add fields to a record. Each field is listed with a name and a data type, and for the traditional value types like alpha, decimal, and integer, a size is also defined. Fields can be declared either directly in a class, or they can be defined within a record or a group within the class. Remember that class members, including fields, have accessibility, and that the default accessibility is private. If you need to access a field from outside the class, then you'll need to change the accessibility to public or protected. Defining records within a class can be a useful technique, as they are very familiar to Synergy programmers and are likely to be used to read and write data from files. You can define records in the same way that you would in a subroutine or a function, with a couple of slight differences. The new optional keyword endRecord can be used to delimit the end of a record. If further non-record field definitions will follow, then you'll need to use the endRecord syntax. Also, you can specify the accessibility of a record, and by default that accessibility will also apply to any fields and groups included within the record. When a class is instantiated at runtime, all non-static class fields are initialized and are commonly referred to as instance data. Each object instance has its own copy of all of these fields. Don't worry about the term static fields right now. Again, that's kind of advanced, and we'll get to that in a future session. Expanding on the customer class that I showed you earlier, here we've added several members, fields in fact. The class now has some attributes. First is a field called account number. Notice that the field has public accessibility, so it can be accessed from outside the class. We also have a public record called address, and 4 fields within that record. Because the record is public, so are the fields within the record, unless the accessibility is overridden at the field level, which in this example it's not. We also have 2 private fields in the class, called loopCounter1 and loopCounter2. LoopCounter1 does not have accessibility defined, so it's private by default. Both of these loopCounter variables can only be accessed by code within methods or properties within this class. But we don't have any such code just yet. So I hear you wanting to ask, what about all the existing records that I have defined in my application, in my include files and in my repository? Can those be used in a class? Well, of course the answer is yes, they can. You can use .include to include record definitions from an include file, and you can use .include repository to include repository-based records. It's not possible to include commons or global data sections in classes, however. These shared data types don't really make much sense in the context of an OO application, where one of the main objectives is to wrap up the data with the code that accesses that data, thereby controlling access to the data. Both commons and global data sections would essentially circumvent most of the additional protections that you gain from the OO environment. Notice that the .include repository syntax has also been extended to allow you to specify the accessibility of the included record, and also to allow the optional end record statement to be added if you wish. This slide shows examples of using existing records within the context of a class. The top 2 show you how to take existing include files and use them in a class definition. Notice that if you want the record definitions from the include file to result in public records, then .define can be used to temporarily change the meaning of the record statement to public record. If you do this, however, don't forget to undefine the record identifier as soon as you're done with it to avoid unexpected behavior later on in the source code. The latter 2 statements include the invoice and item repository structures as INV and item records within the class. Notice the use of the new public and private keywords, which allow you to specify the accessibility of the resulting record. Once a class has fields, the next step is very often to add methods which will be used to manipulate and act upon the values of those fields. Writing methods in a class is very similar to writing subroutines and functions. A method declaration must include its name and its return type. Additionally, it may also include accessibility and some method modifiers and perhaps some parameters for the method. Where subroutines and functions are defined using subroutine proc end or perhaps end subroutine, and functions are declared with function proc end function, methods are delimited with method proc end method statements. As you can see, declaring a method is very similar to defining an external function. Accessibility, public, private or protected, can be specified, along with one or more other modifiers. Method modifiers would be something like static, virtual, override or abstract, but don't worry about these right now. We'll get to all of these things eventually in later sessions. All methods must have a return type specified. The return type could be a value type, like with regular external functions, perhaps a, d, or I, or it could be an extensible type, essentially a class. We'll talk about this more later. If you don't want the method to have a return value, then the new keyword void is used. This indicates that the method does not have a return value, like a subroutine. If the method has any parameters, then these are listed immediately following the method declaration, just like with a subroutine or a function. Remember that strong prototyping is required with methods, so you'll want to use the new parameter definition keywords like in, out, required, optional, and so on, to more explicitly describe how the parameters are to be used. Finally, an mReturn statement is used to return from the method, and if the method has a return value, then the return value is specified as a parameter to the mReturn statement. Unlike subroutines, however, the mReturn statement is optional for void methods. Hitting an end or end method in a method at runtime will do an implicit mReturn. If you do this in a subroutine or a function, it would be an implicit stop, which is generally pretty bad news. On this example slide, we can see a class called order, which includes a method getOrderTotal. Notice that the method returns an implied decimal value. In this case, the method does not have any parameters. It simply acts upon data which is defined within the class. In this case, it adds together the values contained in the three private fields called goods, shipping, and tax. The result is stored in the variable total, which is defined in the data division of the method, just like you would with a subroutine or a function, and that value is then used as the return value of the method. So we add parameters to a method just like we do in subroutines and functions. Parameters are declared, one per line, immediately after the method declaration. As mentioned earlier, Synergy's parameter declaration syntax has been extended to allow for more compile time checking of parameters by allowing you to specify direction, enforcement, and passing conventions. If you don't specify any of these new parameter modifiers, then the default for method parameters is in, required, and by reference. Method parameters can be any supported data type, both value types, alpha, decimal, integer, and so on, and extensible types, objects. Return values include all of those things that can be returned by functions and some additional ones like objects, dynamic arrays, and the special keyword void. Here's an example of a method without a return type. It's a void method. Again, the method acts upon the instance data defined within the class, this time clearing down several of the class's private fields. Notice that there is no mReturn used in this method. There is no return value, so we don't need to use the mReturn statement unless we need to for some other reason. Here's an example of a method which takes two parameters. Notice that the new extended argument syntax is used to define exactly how these parameters are to be used. The first parameter is a required in parameter. It's required, so any call to this method must provide a value for this parameter. The parameter is not updated, it's an in, so either a literal value or a variable can be passed. However, the value must be an implied decimal value because it's an implied decimal parameter. The second parameter is a required out. It's also an implied decimal parameter, so this time a calling routine needs to pass an implied decimal variable, because an out parameter, or an in-out, indicates that the value of the parameter will be updated by the method. Remember, strong prototyping is mandatory with classes, and this allows the compiler to perform all of these validations. With unprototyped subroutines and functions, these are the type of things that tend to show up as runtime errors. Not anymore with methods, or with any other strongly prototyped routine. As well as adding methods to a class, it is also possible to reuse existing subroutines and functions within a class, although there are some limitations which apply when you do so. Of course, in order to be used within a class, existing routines will need to be declared within namespace and class declarations. If you need to continue using the same routine from existing code, then you can .include the routine into the new class declaration code. When added to a class, subroutines and functions become public re-entrant instance routines. Their parameters will default, as they always have, to optional and by reference. If a function does not have an explicit return data type specified, then the return type will be determined by the type of the parameter to the first fReturn statement in the routine. When you later learn about inheritance, you'll need to bear in mind that subroutines and functions may not be overloaded, overridden, or redeclared in derived classes. If you need to avoid any of these limitations, then you could consider changing the subroutine or function to a method. Here's an example of adding two existing subroutines to the order class. As you can see, the add to order subroutine is entirely defined within the source code of the class, whereas the confirm order subroutine is .included from its original source file. The final type of members that we need to know how to add to a class are properties, which are delimited by the property and end property statements. Each property is assigned a name and must have a data type defined. Optionally, the accessibility of the property can be specified with public, private, or protected modifiers. Remember that the default accessibility is private. Properties can also have other modifiers defined, like virtual or abstract. You can learn more about these in later sessions when subjects like inheritance and abstract classes are introduced. Within the property, we define the accessor methods which execute when the property is referenced. There are two possible accessor methods, called get and set. The get method executes whenever the value of the property is referenced by code, and the set method executed when the value of the property is changed by other code. When implementing a property, the programmer must decide how the value of the property will be propagated within the object. Very often, a property will store its value in a private field of the same data type as the property. So, each property can have either a get method, or a set method, or both. Properties are accessed just like fields would be. In other words, to other routines or classes, a property appears just like a field. The value of the property can be referenced or changed. The get method executes when the value of the property is referenced by other code. The job of a get method is to return the current value of the property via an mReturn statement. Remember that including a get method in a property makes the property readable. The set method executes whenever the value of the property is changed by external code. There is a special keyword called value which is used in a set method to access the new value that is being set. So the job of the set method is to take this value and store it away somewhere for later use. As mentioned earlier, a private field is often used to persist the data for a property. The presence of a set method in a property makes the property writable. If no set method is present, then the property is read-only. Every property must have either a get method, making the property readable, or a set method, making the property writable, or both. In this sample code section, you can see a read-writable property called discount%. Notice that the property has a data type of D2. Externally, this property appears like a D2 field. The property has both get and set methods, meaning that the property is readable and writable. You'll also notice that the class includes a private D2 field called discount. This field can't be accessed externally because it's private. The field is used to persist the property's value. The get method simply uses mReturn to return the value of this private field. The set method updates the value of this private field using the special keyword value. You'll also notice that the set method also includes some logic which first validates that the new value is within a specific range, 0 through 20 in this case. The ability to perform validations on values is one good reason to use a property instead of a public field. Note that in this example, if a new property value is outside the acceptable range of 0 through 20, nothing happens, and the new value is simply ignored. In a more realistic scenario, it's possible that the set method would throw an exception if some validation failed. That exception could then be caught by the calling routine. Here is another example of a public property. When this property is referenced, the value that is returned is calculated from various private fields in the class. The opportunity to perform calculations when a property value is referenced is another good reason for using a property instead of a simple field. You will also notice that this property does not have a set method. This means that the value of the property cannot be changed externally. It's a read-only property. Hopefully now you are starting to understand the importance of accessibility, which can be used to hide things that you don't want to show outside of the class. As a review, default accessibility within a namespace is public and within a class is private. Also remember that fields in a record will default to the record's accessibility, but can be overridden on a field-by-field basis. In order to be compilable, each Synergy source file must have at least one procedural section. On occasions, you may need to design a class which has only data, but no procedural members. You can achieve this by adding an explicit constructor to the class. Constructors will be discussed in more detail later. Also, remember that strong prototyping is mandatory for classes. If a class is not local, i.e. it's not included in the same compilation unit as the code using the class, then you must export prototype information for the class and import that prototype information at the point where the class is used. We'll look at how to do this next. Prototype information is exported using the DBL Proto utility. You can use the utility to export prototypes for a single source file, or you can use wildcards to tell the utility to create prototypes for multiple source files at the same time. By default, the prototype utility will create a prototype file for every class, structure, subroutine, or function being processed. Prototype files have a .dbh file extension. So, the DBL Proto utility creates prototype files based on the content of one or more source files. There are several different ways that you can tell DBL Proto where you would like it to create those prototype files. By default, prototype files will be created in the default directory. However, it's likely that you'll want to set up a specific folder to just contain prototype files. You can achieve this by setting the environment variable sin_exp_dir. If set, this is where all prototype files will be created. There is also a mechanism to allow you to specify the output location for prototype files on the command line using the -expdir qualifier. This mechanism will also override the sin_expdir location if set. Every class must be explicitly defined within the context of a namespace, but using namespaces with subroutines and functions is optional. If you want to take advantage of the many benefits of strong prototyping with your own subroutines and functions, then you need to add those subroutines to a namespace and create prototype files for them too. There are several ways to add subroutines and functions to a namespace. Of course, you could edit the source code and manually add the namespace and namespace statements around the routines, but that could affect other places that you're already using those routines from in your existing applications. To help you get around this, you can use the sin_def_ns environment variable, which allows you to specify the namespace to be used for non-class subroutines and functions if a namespace is not explicitly specified in the code. There is also a dblproto command line option called -out, which allows you to do the same thing, and again this will override the sin_def_ns setting that you may have. If you do not take any action to define the namespace for regular subroutines and functions, then the default namespace of sin_global will be used. After using dblproto, you'll see files with these kinds of names in your export directory. By all means, look at the prototype header files, but I would suggest not modifying them, since the next time you run dblproto, it will overwrite any changes you may have made. I would suggest that you get into the habit of running dblproto as part of your normal build process. On this slide you can see an example of what a prototype file looks like for a very simple class. You will notice that the content of the prototype file looks kind of like the original class, but that there is no implementation code present. In other words, there are no procedure divisions in any of the methods, subroutines, functions, or properties in the class. The prototype file is used by the compiler and provides all of the information that's needed by the compiler in order to validate that all external references to the class are appropriate. For example, the prototype allows the compiler to check that calls to the method include the correct number of parameters and that appropriate data types are being passed to those parameters, and that property references are of the correct data type, and that read-only properties are not being updated, and a whole bunch more. Well, we've now covered the basics of how to define namespaces and classes in Synergy, and how to implement those classes by adding fields, methods, and properties. What we really need to know now is exactly how to use those classes in our applications, and that's what we'll focus on now. The process for using a class is fairly straightforward. First, if the class is not local, you need to import the namespace which contains the class you wish to use. The next step is to declare an object variable of the type of the class. Once you have an object variable, you can use a new statement to create an instance of the class, an object. Once you've created an object, you can begin to interact with it by referencing its fields and properties and calling its methods. All interaction with the object is achieved via the object variable. Finally, when you're done with the object, you dereference the object variable from the object. We'll talk more about exactly what that means in a little while. So, the first step to using an object is to import its class's namespace. This is achieved using the import statement. Notice that all imports take place at the namespace level. You don't import a specific class, you import the class's parent namespace, making the symbols for everything in that namespace available in the source code module. Import statements must appear at the very top of a source file, before any other statements. The only exception to this is that comments may precede the import statements. The scope of an import is the entire source file, So if the source file contains multiple routines or classes, the contents of the imported namespace may be used in any of those routines in that source file. The location for the prototype or header files to be imported can be specified in several ways. By default, the compiler will look for prototype files in the current directory. This can be overridden in code via the optional directory qualifier on the import statement, or by using the new q-impdir compiler directive. Most often, it's likely you'll want to have a single location for the storage of all prototype files, and if this is the case, then you can define the sin-impdir environment variable and point to its location. You don't always have to import, but it's a good practice to get into the habit. If you're using non-local classes, structures, or routines, you have to import so the compiler can resolve references to that class or structure. Even if you have the items that you want to use defined locally, you still may wish to import. For classes and structures, importing ensures that the prototypes for those items match the actual declarations of those items. And with subroutines and functions, importing tells the compiler that you wish to strongly prototype those items. Note that if you've chosen to specify the default namespace to be used via the sin-defns environment variable, then you don't actually need to explicitly import that namespace, because it will be automatically imported by the compiler. However, I would recommend that you add explicit imports to the code, because it makes the code more complete and potentially easier to understand and maintain. Okay, let's add a couple more terms to our toolbox. We already know that an object is a runtime instance of a class. A class is a piece of source code that describes a set of attributes and behaviors, and an object is a real instance of one of those things. An object is something that physically exists in memory at runtime. An object variable is a variable that's used to represent an object. Objects can't be accessed directly. They're accessed via an object variable, in the same way that a file can't be accessed directly. It's accessed via a channel number. Object variables are defined in the data division, and they're usually defined as being a specific type. This type is a class name, and is expressed with the @classname syntax. We usually declare separate object variables for each object that we want to create and use. Declaring an object variable does not create an object, like declaring a channel number variable doesn't open a channel. Before we can use an object, we must create it and associate it with an object variable. This process is usually called instantiating an object, or, put another way, creating an instance of a class. This is done using a new statement. It is important that you understand the difference between classes, object variables, and objects. At the top of the diagram, you can see a class called person. The class is the source code that defines a set of attributes and behaviors. If you want to use that class at runtime, then you must define an object variable of the type of the class, and then instantiate an object. If you need to work with multiple instances of the class, multiple objects of that type, then you need to declare multiple object variables, one for each object that you wish to create. In the center of the slide, you can see that we've defined 3 object variables, which we can use to refer to 3 separate objects. When we're ready to work with an object, we instantiate it and associate it with an object variable. Ultimately, our 3 object variables could be used to refer to 3 different instances of the person class. There's nothing particularly special about object variables. They're defined in the data division like any other variable. What makes a variable an object variable is its data type. Whereas a normal variable might be defined as an A10 or a D6, an object variable's type is expressed as @classname. In this example, you can see that we've declared an object variable called customer1, and its data type is expressed as @customer. This object variable customer1 will be used to reference an object of type customer. Customer is the class which is being used. Notice the import statement at the top of the source code. We can derive from this that the customer class is actually part of the mycompany.ar namespace. It's also possible, if you don't care what type of class is passed at compile time, to define an object variable as @star. This variable can point to an instance of any kind of object. It's recommended that you use specific types for object variables whenever possible, since this allows the compiler to do more checking at compile time. With untyped or weakly typed object variables, as they're also known, there is a much higher possibility of errors showing up at runtime. Once we've defined an object variable to represent an object, we can go ahead and actually create or instantiate the object. We do this with the new statement. Immediately following the new statement is the name of the class that we're trying to instantiate. The new statement returns a new instance of that class, an object, which we then usually assign to an object variable that we've declared to represent the object. From that point on, we'll use the object variable to interact with the object. Notice that it's also possible to specify parameters following the class name. This is how you would pass parameters to constructor methods that the class may define. But let's not worry about that right now, because we really haven't talked about constructor methods at this point in any great detail. We'll cover this in a later session. You will notice though that the parentheses following the class name are not optional. Even if you're not passing any parameters to a constructor, you still specify opening and closing parentheses after the class name. Each time you use a new statement, an object, an instance of a class, is created in memory. The new object's instance data is initialized, and one or more constructor methods may execute. Again, more on this later. Whenever you use a new statement, you will always want to assign the created object to some object variable. Otherwise, the object will be created and then immediately deleted again. Once you've instantiated an object with the new statement and assigned the object to an object variable of the correct type, you can then begin interacting with the object as required by your application. Perhaps the simplest thing to do is refer to or change values associated with the object's fields. To refer to a field, simply specify the object variable name, followed by a period, and then the name of the field that you're trying to access. In this example, we've declared an object variable called obj as type myClass. We then use a new statement to create a new object of that same type and associate the object with the object variable. This is called instantiating an object. The statement obj.SumField equals 5 updates the value of the object's SumField field. The xcall statement is passing the value of the SumField field as a parameter to some subroutine. Remember that in order to be able to interact with a field in this way, the field must have been explicitly declared as public. Another thing we might want to do with an object is call its methods. Again, we use the object variable followed by a period, and this time followed by the name of the method. There are a couple of slight differences from calling subroutines or functions, however. Notice that there is no xcall or % syntax used to call the method. In fact, from version 9, the use of xcall and % is even optional when calling subroutines and functions. You'll also notice that, again, the open and close parentheses are required, even if you're not passing parameters to the method. So, the example code at the bottom of the slide instantiates a myClass object and then calls the object's SumMethod method. Presumably, this method is a void method, or in other words, it does not have a return value. If the method did have a return value, then we could assign the return value to a variable or embed the method call in another expression, just like you would with an external function call. Finally, we need to know how to interact with an object's properties. And actually, this is kind of a non-event for us now, because to all intents and purposes, properties appear to the outside world just like fields do. we refer to them in just the same way. Remember that differences exist under the hood though. Although we use a property like we would a field, we now know that the properties get and set methods are actually being executed under the hood in order to return or accept the property's value. Also, remember that properties might be read-only and in rare cases might be write-only. Finally, when you're done using an object, you should dereference it. This is usually achieved using the clear statement, clearing the object variable. Dereferencing an object is not the same as deleting an object. We'll explore this again or in more detail in a few moments. Bear in mind that in some cases, implicit dereferencing of an object might take place. For example, if an object variable is defined in an external subroutine or function, or in a method, and that routine returns without explicitly dereferencing the object, then the object could be implicitly dereferenced as its object variable has now gone out of scope. An object can also be dereferenced if a second object is assigned to the same object variable. An object variable can only ever be associated with a single object, so assigning a new different object to an object variable will implicitly dereference any object that was previously associated with that object variable. There is also an additional way to dereference an object from an object variable, which is to explicitly assign the special value of #null to the object variable. Clearing an object variable and assigning a value of #null to an object variable are exactly the same. It is really very important that you understand the concept of object variables and objects. They're really not the same thing. An object variable is a variable which points to an object. It contains a reference to an object, but it is not the object. An object is something which exists in memory and can only be accessed through an object variable. An object variable can only be associated with one object at a time, but an object can be concurrently referenced by several object variables at the same time. Each object keeps track of how many object variables are currently associated with the object. This concept is usually referred to as an object's reference count. Dereferencing any single object variable from an object does not necessarily mean that the object will be deleted. An object is deleted only when its reference count drops to 0. I know that for some of you this may be a difficult concept to grasp, but with experience it will become second nature. To try to demonstrate the concept of reference counts and object lifetime, consider the following example. The code on the left declares two object variables, obj1 and obj2. The code then instantiates a new object and associates it with the object variable obj1. Then obj1 is assigned to the second object variable. With object variables, this does not copy the referenced object. It creates a second reference to the same object. The code then dereferences the first object variable, obj1, and then the second object variable, obj2. Let's take a closer look at what that means in terms of what objects are created and deleted. The new statement creates a new object and associates it with the object variable obj1. The statement obj2 equals obj1 creates a second reference to the same object. The object now has a reference count of 2. Then the original obj1 object variable is cleared, dereferencing it from the object. The object now has a reference count of 1. Finally, the second object variable is cleared, removing its reference to the object. As a consequence of this, the object's reference count has now dropped to 0, and therefore the object has been deleted. Clearing any one object variable does not necessarily cause an object to be deleted, ever. The only thing that causes an object to be deleted is when its reference count falls to 0. Please remember that at this point we're really only scratching the surface. There is a lot more to talk about, and we'll do just that in subsequent sessions. Information about OO support in Synergy can be found pretty much throughout the language documentation. I've listed here some of the main areas of the documentation that you might want to visit and review. Well, that's where we're going to wrap things up for this first session on developing with OO techniques in Synergy. In this session we've introduced some of the main OO terms and hopefully explained what some of those terms mean. In the session we focused on basic classes with fields, methods and properties, and looked at how objects are created, used and deleted. There are 2 more presentations in this series. In the second presentation we'll introduce yet more OO terms and capabilities like method overloading, constructors, destructors, static members and more. And in the third presentation we'll introduce inheritance.